Hello, welcome to a new chapter. Now we're ready to start exercise 1. Section A tells us that we have this Lagrangian and is find the Euler-Lagrange field equations in the following cases. Okay, so the action will be d for x and this Lagrangian. 1/2 partial mu phi of x partial mu phi of x minus m squared over 2 phi of x squared. And in order to do this kind of calculations, let's remember two properties that for sure will help us a lot in this chapter. Remember, if you want to calculate the functional derivative with respect to fy of something of this form, derivative of f with respect to x times whatever you want to put here, then remember that this was minus delta x minus y times the derivative of g with respect to x, of course. And if you find some expression in terms of a function, in this case, this would be g of phi defined as m squared over 2 phi of x squared. So the functional derivative of this expression would be Dirac's delta times the partial derivative, the normal, so to say, derivative of g with respect to f. Remember, if you want to find the Euler-Lagrange field equations, one way to do it is by means of calculating the functional derivative of the action. Let's call this s. I know Santi called this I like more to say this is s of phi. So, in order to find the Lagrange field equations, you must calculate the functional derivative of this action with respect to phi y and then make it equal to 0. This is the rule. So, let's see. First of all, we can compute the functional derivative with respect to phi y of 1/2 partial mu phi of x partial mu phi of x, namely this first term. So looking, let me write 1/2 before I forget that. By the way, the chain rule works here. The functional derivative with respect to f of a times b is the functional derivative with respect to f of a times b plus a times the functional derivative with respect to f of b. I mean, the chain rule. So this will be the functional derivative with respect to phi y of partial mu phi of x times this term plus the first term that stays the same times the functional derivative with respect to phi y of partial mu phi of x. But as we will see, it's convenient to rewrite this thing. This stays the same for the moment, but it's convenient to move this guy to this position. You will see why. 1/2 partial mu phi of x. So we can delete this and let me hide these properties to make some space. So we have this and now we're ready to make this equal to what in fact is. Remember, the first property say that this is minus delta g prime. So this will be minus delta x minus y and this partial mu acting on whatever is in here. So partial mu phi of x. And the same thing applies here. So this is going to be minus delta x minus y partial mu, but with the index upstairs, acting on 1/2 phi, times partial mu phi of x. So let's put this 1/2 here, 1/2 with the minus. But remember, we are dealing with tensor objects. If you come across something like this, a mu, b mu, this is the same as a mu, b mu. So we can lower this index and raise this index. because it's the same. Sorry, there is a missing minus sign, sorry. Okay, so this term is equal to this term, so we have this term twice. So this 2 cancels out this 1/2. So we finally have minus delta x minus y partial mu phi of x. And let's calculate the derivative of the second term. So let's do it. The functional derivative with respect to phi y of minus m squared over 2 phi of x squared. And this is going to be, first of all, minus m squared over 2 times the partial derivative of this function, of this expression, 2 phi of x times delta x minus y. This delta comes from the functional derivative of phi of x with respect to phi y. This is the origin of this Dirac's delta. If we put this here and deleting this 2 with this 2, now we can say that it means that if you want to compute or to calculate the functional derivative of the action, namely the 4x here, then you need to write the 4x here. But remember, this delta cancels out this integral, but when you write the final expression, partial mu phi, is phi of y, not x, because of this y here, plus m squared phi y equals 0. And of course, this partial derivative means the partial derivative with respect to y mu. But once you obtain this, you can change the name and write x instead of y. I use y for the calculation. So don't forget to make this equal 0, because we need to do it if you want the Euler-Lagrange field equations. So the final result for section A is this, with x if you want. Now let's go to section B. First of all, if you come across a thing like this, phi star, then it means that you have a field of x that is formed by two functions. Let's call it u of x plus I v of x, and of course phi star means that you have to conjugate this field and you will obtain u of x minus I v of x. And if you perform partial mu phi star partial mu phi, you will have partial mu u minus iv because of this star, partial mu u plus ib, and if you expand this will give us partial mu u minus I partial mu v times the same thing, the similar thing to this term. And if you multiply partial mu u plus partial mu u I partial mu v minus I partial mu v partial mu u, I times I is minus, with this minus is plus, partial mu v partial mu v. This term cancels out this term, and finally we have partial mu u partial mu u plus partial mu v partial mu v. And if you do the same thing, but not only in the kinetical term, then you will have minus m squared u squared plus v squared. This thing stands for this phi star times phi, minus lambda over 4 u squared plus v squared squared. So if you reorder this, you will have partial mu u partial mu u minus m square u square, this term, plus partial mu v minus m square v square. And let's see, the last term is minus lambda over 4 u to the power of 4 plus b to the power of 4 plus 2 u square v square. So let's join partial mu u minus m square u square, and this term also minus lambda over 4 u to the power of 4 plus partial mu v minus m square b square, and minus lambda over 4 b to the power of 4, and the final term is lambda over 2 u square b square, or if you want, I will put it green and v yellow. And this is important because it's the first time we have what is called, and this term is responsible to couple the equations of motion. But the important thing here, this reveals that these Lagrangian have 2 degrees of freedom. So as a consequence, we can treat phi of x and phi star of x as independent fields, because u and v are. So you can follow this way of thinking, performing the functional derivative of the action with respect to uy and make it equal to 0, and calculating the functional derivative of s with respect to vy and make it 0. And then you will have the equations of motion, and then you can isolate u and v to express u and v as a function of phi and phi star. But this is a complicated way to do it, but we can do the same if we treat them as independent fields. So let's do it. So let's start with the field phi of x. Okay, so let's compute the functional derivative with respect to phi y of partial mu phi star partial mu phi n. So the property that we will use is this, but keep in mind that we are performing the derivative with respect to phi y, not phi star. So if you want, we can change the order because these objects commute in order to see more clearly what we are doing. So now, if we apply this rule, we will obtain minus delta x minus y, the derivative of the second term. But the derivative in this case is partial mu. So partial mu acting on partial mu phi star. So if we want to calculate the functional derivative of the remaining terms, minus m squared phi star phi minus lambda over 4 phi star phi squared, then we will have minus m squared. And now the second property tells us that we need to perform the partial derivative of g with respect to the function. So the derivative of this with respect to phi is phi star times Dirac's delta minus lambda over 4. Let's compute the derivative. 2 times phi star phi times the derivative of this expression, so phi star. So let's hide the properties, and then the functional derivative of the Lagrangian density will be all this. And if you want to compute the functional derivative of the action, then you must integrate this, and then putting the integral here, we have this. Sorry, there is a Dirac's delta missing here, sorry. And then these deltas cancel out this integral and change x for y. So finally we have minus partial mu phi star of y minus m squared phi star of y minus lambda over 2 phi star square of y phi of y. And then make this thing equal to 0. So if we change the name y for x and factor out the minus sign, then the equations of motion obtained by means of phi of x will be partial mu phi star of x plus m squared phi star of x plus lambda over 2 phi star square of x phi of x equals 0. Okay, so let's have a look to this before deleting it, because due to the fact that Lagrangian density is real, then if we conjugate the left-hand side of this equation and the right-hand side of this equation, due to the fact that the Lagrangian density is real, the only thing that will change here is this field. And here we can delete this star, this star, this star, and this star, and the only thing we need to do is put in star here. So we just calculated the functional derivative of the action with respect to phi star y, and this is the result. So if we perform all the steps done before, we will obtain partial mu phi without star x plus m squared phi without star x plus lambda over 2 phi without star square plus phi star x equals 0. And these are the equations of motion in this case. This equation and this equation. Okay, section C. Let's write the Lagrangian density first of all. Minus 1 over 4 f mu nu f mu nu minus let me write it like this, with the index upstairs and downstairs here. And of course f mu nu is defined by partial mu a nu minus partial nu a mu. Okay, let's delete this to make some space. So let's remember again the chain rule that applies also in functional derivatives. So if you want to calculate the functional derivative of L with respect to by the way, a mu is the field with which we must calculate the equations of motion, not f. This is an important thing. So we must write here a. But the other thing that you must keep in mind is you cannot write mu or nu here. You must write another index, for example, alpha. This is an important thing. Okay. If we perform the derivative, applying the chain rule, we can write minus 1 over 4, the functional derivative with respect to a alpha. Okay, by the way, a alpha depends on y, and all this thing depends on x. Okay, keep in mind this also. I don't write it in order to simplify the writing. We will write it when we need it. So let's continue. The functional derivative of the first term times the second term plus the first term minus 1 over 4 f mu nu times the functional derivative with respect to a alpha of f mu nu. But remember, you can always raise the indices mu nu in a contraction, of course. But there is a contraction here. So we can change these indices. And this is interesting because now we have a thing plus the same thing. Because remember, all these things are functions and the functions commute. So we finally have minus 1 over 2, the functional derivative with respect to a alpha of f mu nu times f mu nu. Sorry, we need to add this functional derivative, of course. G mu, the functional derivative with respect to a alpha of a mu. Now this is correct. Let's start with this apparently simple expression, and let's do it. The partial derivative of a mu of x with respect to a alpha y is two things. The first thing is delta x minus y. But the second thing is that you need to put delta mu alpha, because only when mu and alpha are equal, then you will obtain something different from zero. This is an important thing you must add here in order to obtain the correct result, of course. So if we substitute here, delta alpha mu delta x minus y, and the only thing we must do now is to calculate this and substitute. So let's do it. Functional derivative of a alpha with respect to y of f, but f is partial mu a nu of x minus partial nu a mu of x. Now we have here two kind of things. The first thing is derivative. So remember, derivative of a derivative is minus delta x minus y, and the derivative acting on the thing you have here. But the thing you have here is f mu nu. So let's write it in order to be more clear. We can write here f mu nu. But remember, we must add delta nu alpha because of this alpha and this nu, in the same spirit that we did 2 minutes ago. So let's continue. So we have here minus, but with the minus that appears in order to do the functional derivative, then it becomes plus delta x minus y times delta mu alpha again, and this derivative acting on f. Let's factor out delta x minus y, and let's see. We will have minus partial mu, and we will write alpha instead of nu because of this Kroneker's delta. So f mu alpha plus partial nu, and in the same spirit we change mu by alpha. But let me put this minus a half here, minus a half. So we will have minus a half. This mu index is mute. So it means that we can change the name and we can put, for example, I don't know, beta. This new index is also mute, so we can change the name. Suppose we rename this as beta also. So if we do this, then we can factor out partial beta acting on minus f beta alpha plus alpha, plus f alpha beta. But remembering that the f tensor is antisymmetric, it means that this is equal to minus f beta alpha, then we can add them, and then we will have this term twice that will cancel out 1/2, and this minus also. So we will have delta x minus y partial beta f beta alpha. So if we substitute all these things for this, we will have delta x minus y partial. Instead of beta, we can write mu, if you want, f mu and alpha. By the way, due to the fact that we have here a delta alpha mu, then this forces this index to be alpha, and now we can factor out delta. So in order to obtain the equations of motion, now it's easy because the only thing you must do is something similar as we did previously, is to integrate this and this, because this is the definition of the functional derivative of s with respect to a alpha y. So again, this delta cancels out this integral, and finally we obtain partial mu f mu alpha minus j alpha equals 0, or f mu nu, if you want, change the name, j nu. By the way, y, but you can also change the name and put x here. So these are the equations of motion, and as you probably know, this is the relativistic way to write the Maxwell equations. So let's do section D, but first of all, I would like to say that there are many ways to do section D, but essentially we can say that there are two basic ways. By means of a certain intuition, and the second way to do it is without, without messing around. So let's start with intuition, and first of all, let me simplify a little bit this Lagrangian density because it will be easier to work with it. Let me define sigma mu as sigma 0, sigma 1, sigma 2, and sigma 3, and sigma 0 is defined also as the identity matrix, so we can define as a 1. So if we define sigma mu, then psi daga partial t or partial 0, because z equals 1 in this case. Psi plus psi daga, this dot product can be written as sigma I partial I psi, and this I goes from 1 to 3. Okay, but with this notation we can see that we can write this Lagrangian density as a partial 0 plus sigma I partial I psi, and if we introduce identity matrix, or in our case sigma 0, because it's the same, because remember I defined sigma 0 as the identity matrix, then all this thing can be simplified to this nice contraction, sigma mu partial mu. So the Lagrangian can be written as psi daga sigma mu partial mu psi. Okay, and remember this also can be written as psi 1 star, psi 2 star, let's see, partial 0, okay, this is the identity, and partial 1 will be partial 1, and partial 2 minus I partial 2 plus I partial 2, and the 3 component will be plus partial 3 minus partial 3, psi 1, psi 2. I show this because this is the nice and simple way to write this complicated thing. So now we are in a similar situation, because now there are 4 fields here: psi 1, psi 2, psi 1 star, and psi 2 star. And we can claim that these fields are independent fields in the same spirit that section B. So you would have to calculate the functional derivative of S, or if you want, of L, with respect to psi 1 and make it equal to 0. The same thing but with psi 2, the same thing but with respect to psi 1 star, and the same thing but with psi 2 star. All these terms must make them equal to 0. So this is the, if you want, the detailed way to do it. Let's think if there exists some simple, intuitive way to do this calculation. So let's see. Let's imagine that this thing makes sense. The functional derivative with respect to psi y. And remember, psi is like a vector. In fact, it's a spinor, but in this context, it doesn't matter. Remembering, let me start with psi dagger. It's better to start with psi dagger. So remembering the second property, whenever you have an expression as a function of the field that you are working on, you must perform the partial derivative. So here we have our field times something that has nothing to do with psi dagger, because in this context we say, or we suppose, that psi and psi dagger are independent fields in some way. So if you perform the partial derivative of this thing with respect to psi dagger, it's only sigma mu partial mu psi times delta x minus y, if we consider this rule is correct, of course. So if you integrate this, d for x, this delta cancels out this integral as usual, and then the final result will be sigma mu partial mu psi y equals 0. So using this intuition, we think the solution of the equations of motion from the derivative of psi dagger is this. Is this correct? It turns to be that yes, it's correct. And we can do the same trick as before, because if we, let me see, let me delete this, and let's move to the right a little bit. If you perform not the conjugation but daggeration, if you dagger this thing, the left hand side of the equation and the right hand side, we will obtain that this dagger cancels out this dagger, and now we must write all this expression dagger. So we will have this. But remembering in quantum mechanics, you know from quantum mechanics that A times B dagger equals B dagger A dagger. So using this property, then we will have partial mu psi dagger times sigma mu dagger. But remember, Pauli matrices are Hermitian, so this is sigma mu. So we finally have partial mu psi dagger, because the partial derivatives are real in some sense. So we will have this. And then if we make this equal to 0, then we will have another equation of motion. And also it turns to be that this is correct. The funny thing is that this intuition gives us the correct equations of motion. So exercise. Expand all this expression, the Lagrangian density, and check that the equations of motion that you will obtain are the same as these equations. This is important because if you continue with quantum field theory in the next semester, you will see this in the context of Dirac's equation. So I encourage you to do it. So that's it. Thank you for watching this video and see you soon.